I can't hear you yet. Let's see. This is...
Can you hear me now?
Now I can hear you.
Okay, great.
Good.
Perfect.
Great. How are you?
Pretty good. And yourself?
Good.
Nice.
You're in New Jersey?
Yes.
Great.
I'll be here for a while, probably for the next few months, I believe.
Good. Hey, Deb.
Hi, Deborah.
Can't hear you yet.
Oh,
Now we can.
can you hear? I'm not on, okay?
Yeah.
You're good? Yep. All right.
Yep.
So two things.
Hi, Ryan.
I'm not gonna be here next week.
Okay.
You guys do one great, but I now know why I didn't remember this sequel, because it's kind of not that memorable in certain kinds of ways. Although
Okay.
I did see it once before, but I think there are obviously things for us to talk about. So
Yeah, definitely.
leave it. Throw it to you.
I learned that this is actually a prequel to a new series, which is the Alien series, and there are like a few more movies after this. So not only is it a sequel to Prometheus, but it starts like a whole new cycle of Alien series movies. I thought that was pretty interesting.
All Ridley Scott.
Yeah.
I would not want to live in his head. What is he on about?
Yeah. First, I want to, before we get into the PowerPoint, I want to show just the panorama view of, this is the Curiosity rover. Hold on. I wanted to find the 360 rover Perseverance view. And I think there's like an interactive thing where you can scroll around.
Oh, this is the one that's flying around up there in Mars?
Yeah, this is the drone that's hovering above
The helicopter?
the helicopter, yeah.
So how does it do that with such a thin atmosphere?
Yeah. I believe the thrust has got to be a lot more, and also the blades are probably a much bigger surface area. Let me see if I can find an image of the drone itself.
We had it earlier.
There. So it's extremely lightweight, I'd imagine. And then you have these dual blades that are probably spinning at a really high rate. And
So you said
also,
Perseverance, but this is Ingenuity?
so the Ingenuity is the name of the drone. And then Perseverance is the rover. The rover is going to carry the drone. And it landed with the whole package. So this is Perseverance, the whole rover that's on the ground. And then Ingenuity is just the little drone that flies up. So let me see if I can find a nice picture here. Go like, interestingly, you can't like scale these up. These are very, very small pictures. But the Curiosity rover, I think, had a nicer 360 view. Let's try one more time. It's pretty much the same kind of resolution. So I really liked this one before. No, not this one. Where was I? Yeah, so this one you can zoom in. This is like super HD. This is the one I was looking for. Yeah, you can zoom in a lot. Really high quality photo here.
Mm.
This is just the landscape of Mars.
This is from Perseverance.
This is
So this is a
this
remote
is Perseverance.
camera on one end of it.
Yeah, so there's a camera sticking up and it's like a ball shape. So it's
Yeah.
looking 360 degrees around.
Wow.
So this is like the back side of the rover over here, looking backwards, and then this is all the way forwards. You can see just like all the massive instruments in here, the wires. So yeah, this is what's currently sitting on the surface of Mars, taking tons of data for us.
So walking on the planet.
And you notice like even, yeah, go ahead.
I say walking on the planet, it's
Walking
kind of
on the
like
planet.
walking on some parts of Earth, but I guess the temperature would be very different, and you couldn't breathe out there without a spacesuit, right? I mean, there's like Zippo,
Exactly.
and you would die. Is there other reasons you would die besides the air and the temperature? The air not having enough oxygen in it
Radiation?
immediately?
The radiation, I think, would still be pretty slight. Mars is pretty far away from the sun that I don't think it would be a major factor. But the temperature first, yeah, will be, colder than Antarctica at some parts of the day. And then, yeah, there's no oxygen, and there's a lot of carbon dioxide, but there's not a lot of either. The atmosphere is very tenuous, and there wouldn't be enough pressure for you to get any of those gases in your lungs. So you'd be really trying to suck in wind, if at all.
It doesn't.
But yeah, even though the atmosphere is super thin.
Go ahead. Even though
Oh
the
yeah, I was just
atmosphere-
gonna say, like, yeah, it's even though it's really thin, like it's still opaque. It's this pale yellow color that you can't even see through.
Mm-hmm.
So you can't even see the sun, even though it's broad daylight out. It's like almost a dust storm covering.
Is it because there is an effective dust storm, or is there something else that's causing the yellow?
So some of it, I guess, would be from just normal refraction, like the reason our sky is blue. So this one is like a whitish yellow. But yeah, dust constantly gets kicked up from the surface because it's incredibly dry. There's really no liquid anywhere.
This is like you were talking
so
about
yeah,
last
dust
week.
storms.
This is like the moon. You were talking about that last week with the moon.
Yeah, the moon is even drier. The moon is like abrasive. It's so dry.
So the texture of the surface is really interesting with, with this ground down sand and dust, and then more solid pieces sticking up through
Right.
it.
Uh-huh. So yeah, I mean, this could be signs of erosion. Like you have these like finer particles, scattered along the landscape. We don't know. It could have been like covered in ice at one point. We still have two major ice caps at the poles. But the geology of Mars is, not fully understood, especially billions of years ago. And the wind is definitely a factor. If there's enough wind to kick up sediment, you're going to have erosion over millions and millions of years.
There's no magnetic field there anymore, or very little, right? That's why it
Very
doesn't have
little,
an
if any.
atmosphere.
Yeah, I'm not quite sure. Like, I wonder what the core of Mars is like. I think it does have a little bit of a magnetic field. Let's check it out. Mars does not generate a magnetic field on its own, outside of small patches of the crust, which are magnetized, apparently. And yeah, I think it is due. So the reason it doesn't have an atmosphere, or very little, is the magnetic field has gone away. So the atmosphere got stripped from the solar radiation.
What is first map of Mars electrical? That's a great YouTube.
Yeah.
Mars electric currents. Maven.
Okay, so here's, I guess, what it looks like. They're going to cut it open. And this is sort of the same thing that happens to Earth. You know, we get solar wind coming to the planet, we get bombarded, but we have a really strong magnetic field. So a lot of the solar wind passes right over us, and we are unaffected for the most part, except like at the poles, the solar wind can sneak its way in, and we have the aurora, the northern lights. Yeah, so this is I guess the current flow on an ancient Mars. So perhaps billions of years ago, when it had a stronger magnetosphere. So, all right, let's go here. This is the title slide. And we have the alien monster, which is, I think, what makes it a horror film as well as a sci-fi film. Let's dive right into it, because they start off the movie trying to find a habitable place to colonize. And, this is a huge topic in astronomy. Viable candidates for exoplanets that look like our home. And I thought it'd be really cool to talk about the methods we use to find exoplanets. So the first thing we can do is look for a Doppler shift. And what this is we look at a host star that is probably having planets orbit it, and we look for a little wobble back and forth. And if the light from that star is blue shifted and then red shifted and then blue shifted and then red shifted in a regular period, that means something is making the star wobble back and forth toward us and away from us, toward us and away from us. And we can deduce, okay, a planet is tugging on that star, and we can measure how much that shift in color or shift in wavelength is, and figure out how massive and how nearby the exoplanet is. So I want to try to find maybe an illustration here. Yeah, oh, this is tiny. So this star is what the exoplanet is orbiting around. And then as it's moving toward us, the light from that star is shifted into the blue. And that's the result of the Doppler effect. Just like with sound pitch getting higher as the source is approaching you. And then it gets redshifted as it moves away. And that's because the exoplanet is moving the star back and forth. So that's just one method on how we find exoplanets. And I'll leave you with a quick question. So there's a bias. We find that a large fraction of the exoplanets we detect are very massive and very close to the sun, or their sun, their host star. And we call them hot Jupiters.
Yeah.
And can you think of why we find a lot of hot Jupiters? Something like this.
When that last when that last speaker series person spoke last week, was it?
Yeah, last
She
Friday.
mentioned this, and yeah, and so I was wondering, how can you have a gas giant closer to a heat source, a sun, a personal sun? Wouldn't the gas just boil away? That she mentioned hot Jupiter's closer to their sun than Mercury is to
Right.
ours. And
Yeah.
I found it kind of, Boyle's law curious.
Yeah.
I mean, are you trying to, it's not just, you're not trying to just get at the size issue.
Yeah, sort of just like
Like they're big, so they're going to make, more of a Doppler effect or any other kind of effect. These gigantic.
that's right. Yeah. So the reason we find a lot of hot Jupiters is when we use the Doppler effect, the big close by planets are going to be the ones that we detect first and most frequently. Because a bigger wobble is far more noticeable than a little wobble. So the planets that may be contributing just a little bit get overshadowed by these hot Jupiters. So here, Deborah, there's a little section here that these hot Jupiters do actually lose their atmosphere.
Yeah.
And so it depends on how big it is to begin with.
Lowest it's, yeah.
So they can lose.
Oh, yeah. So this is all under the hot Jupiter.
Yeah. So this is
Yeah.
just a subtitle. Yep.
Yeah.
So anything closer than 2/100ths of an AU, which is basically 200 times closer than Earth is from the sun, then the atmosphere is going to evaporate pretty quickly. So
Yeah.
it says,
Yeah, and the previous window, but the previous window, it said something about they don't have much of an eccentric orbit. So does that mean they'd have less wobble? Or this is just even going around a perfect circle? That you'd have the Doppler effect.
yeah. So, yeah, that's a good question, because anything with a high eccentricity is going to make that wobble more dramatic.
Yeah. It's, yeah.
So yeah, it's kind of interesting how most of them have circular orbits. But I would imagine that if something does come that close to a host star, its orbit is going to be pretty circular. And you can kind of see this with the solar system. if we zoom out, you'll notice that the terrestrial planets and like Jupiter, Saturn have pretty circular orbits. But then as you go out to Pluto and beyond, some of the orbits are hugely eccentric. And as a result, the periods are on the order of hundreds, possibly thousands of years.
Uh-huh.
Yeah, here we go.
Oh, really?
So everything, so I'll just show back-to-back images here. These are the first few planets, Mercury, Venus, Earth, and Mars. And Mercury, well, yeah, Mercury is pretty circular, although this could be exaggerated. Venus and Earth are pretty perfect circles. And then you go out to Sedna and all of these other dwarf planets and asteroids just have complete ovals stretched out like this. So I think proximity is an indicator of how eccentric that orbit is. The closer you are to your star, the more circular your orbit should be. But there are a few other ways we can detect exoplanets. And the other way is the transit method. And transit just means that the exoplanet passes in front of its host star and we see a dip in brightness. So, and it doesn't even have to be that substantial. For example, this is like the transit of Mercury a couple of years ago. Just this little dot passing in front of the sun. And you really get an appreciation for how massive the sun is compared to Mercury. And Mercury is, not much bigger than our moon.
So you'd find a very tiny diminution of brightness.
Exactly.
With that transit.
Yeah. So we detect there's something moving in front of the star we're looking at when we look at the brightness over time and it's like a pretty steady line. And then all of a sudden it drops a little bit and then it goes back to normal. The key thing is that this drop in brightness happens at a regular interval. So,
like if you had a black, what we perceive to be a black sunspot, would you see a diminution in brightness?
a sunspot?
Yeah.
Yeah.
Because they're depicted as black against the yellow sun, and even bigger than that. So, do you see a diminution of brightness with them?
I would imagine, yeah. So if there's a large enough sunspot, let's say you were watching the sun over time and the sun rotates, and let's say on one side you had a whole bunch of spots, and then the other side it was pretty clear. Yeah, the brightness would be a touch, very minuscule, but I would imagine it would be less than the clear side.
How
However,
long does it take for the sun to do a full rotation?
it's a good question. I'm not sure. Maybe it's a day. Let's see.
No.
How much? 25 days. 25 days. So, I mean, that makes sense because the sun is enormous. It's 1,000 times the diameter of Jupiter, 1,000 times the size of Jupiter. And Jupiter goes around in about 10 hours. So yeah, sun is much slower because it's much larger. 25 days, so almost our month.
So why is Jupiter 10 hours and Earth is 24 hours?
It's kind of just a game of chance. When the early solar system formed, things were flying around at all different rates. Venus, even though it's about the same size as Earth, is exceptionally slow. It takes longer to spin around its axis than it does to go around the sun once.
Wow.
So that's like 200 something days, I believe. In fact, Venus walks, this is a cool fact, Venus rotates so slowly that if you were to walk on its surface, you could watch a infinite sunset just by walking, because you would be matching the rotation rate of Venus. So the sun would never set if you just walked in its direction.
Wow.
But going back to just like that dip in brightness, sunspots may dip the brightness a little bit, but compared to what we see from a whole planet passing through, this is sort of what we expect to see. So pretty constant brightness, and then, a planet moved in front of it, and then it went away. And we see this like a regular period.
Mm-hmm.
This is what it would be like if we saw Jupiter from another star system. This is how big the transit would be.
They have other little dots on that. Was that supposed to mean Earth and,
No.
Two of its moons, in fact.
Oh, those moons of Jupiter.
Yeah.
Oh, wow.
And
So
then
probably-
beyond that are sunspots.
Yeah, the sunspots are over on the right.
Yeah.
These little like irregular shapes, but then the two dots, the circles, that's probably Ganymede and Callisto or something, maybe Io.
So this is just a computer generated?
Yes, this is what it would look like if I had my telescope in another star system and looked at our solar system.
Right.
And say, oh, look, we have exoplanets.
Mhm.
But it's not a hot Jupiter. It's a cool Jupiter, because our Jupiter is like 1 billion miles. No, it's 500 million miles away from the sun. Saturn is 1 billion miles, I think. I got to make sure I get my distances correct. And this is like the period that we would, oh no, wait, no, this is the Doppler method. Sorry. Anyway, then there's one more. This is probably the trickiest method
Gravitational lenses.
to find exoplanets, the bending of space-time. So getting into some general relativity here. So we have the source star, which is not the star that the planet's orbiting around. We detect the planet not by looking at its host star, but by looking at a different star even farther away. And it's got an apparent position that's different from its actual position. And the reason it's got a different position in the sky is the planet's bending the light. Well, the planet and the star, but the planet is making it like a little more than we expect. So we have a certain expectation for how much the light should bend if it was just the star bending the light. And then we have a little other piece that the exoplanet's responsible for. This is probably like super difficult to orchestrate, to figure out. I was like, okay, I got to find a star directly behind the one I'm exploring. And I have to look for this, infinitesimal shift in the apparent position of that distant star. So
Well, in that, you'd have to anticipate an occultation.
yeah. So it's crazy. This is like the data that astronomers are given, and the star that the arrow is pointing to, it's not supposed to be there. That's not its actual position. It's really, a few arc seconds or whatever to the right or left. And you have to take data over and over. You get like days at a time. You have to track the position of that little star and watch it wobble. Not physically wobble, but the light from it getting bent.
I have a question about the Doppler effect, in that we describe stars seen as yellow or blue or red.
Yeah.
And and what Sam has said when I've asked the question, maybe I was just indirectly alluding to the Doppler effect, but that was what was in my mind. And he said, no, it has to do with the temperature or the age. But in my mind, I was thinking, is that color because of the Doppler effect? When you describe stars, of different colors.
Okay,
So,
I understand. Yeah. So the color that like you see with your eyeball and you say, okay, that's a red star, that's a white star, that's a blue star. Depends on the age and temperature. Your eyeball won't be able to detect the Doppler effect. Because
so it doesn't see it as, okay, go ahead. It doesn't see it as red because of it's moving away.
Right. So the Doppler effect shifts it by like a few nanometers. Your eye can't detect that. It goes from like red to a tiny bit less red. And we call that a blue shift. So it could be a little misleading because you don't measure the Doppler effect with your eye. You measure it with like an extremely sensitive instrument. If you were to go over to the electromagnetic spectrum, and let's say you have a bright blue star, it's like right in the middle, and let's put a number on it. We'll say it's 499 nanometers, and then it gets blue shifted a little bit more, and now it's 502 nanometers. To your eye, it's still going to look bright blue. There's not going to be a difference in your perception. Yeah, that's a really good question because I know that tripped me up a little bit when I first learned about this in undergrad.
Okay. Thank you.
Yeah. So those are like the three main ways of detecting exoplanets. And you can also do direct imaging if you have that luxury, if it's near enough and you can say, oh, look, some light is being reflected off its surface. I can just see it with my own telescope. That's great, but it's usually not the case where we're that fortunate.
So which of the, this physicist, astrophysicist that Deb mentioned earlier that did the talk last Friday, they're trying to get this thing called LUVAR. It's a next generation space telescope.
Oh, is it going to replace the Hubble?
Well, James Webb is going up in the fall, and this one they're just trying to get funding for. They don't have a way to get it up yet, but if you look for it, LUVOIR, I think it would.
Yes.
I'd be curious what.
I wrote it down. Yes.
I can't remember which of the three methods it was. Yeah, LUVAR.
Okay. Yeah.
So that's using which of the three?
Oh, that'll probably be best for direct.
UV.
Yeah, direct imaging and possibly the Doppler method. And you can also use this for the gravitational lensing. Gravitational lensing, you just need light of any wavelength, really. We can see most of the stars. So yeah, this is going to be like a broad optical telescope. So we're going to have like phenomenal images probably. So, our eyes go from very deep red to very bright blue violet. This is going to like be a wider field of view. It's going to
They're going to use all three methods you mentioned.
Yeah.
Gravitational lensing and transit and Doppler shift.
Yeah, this is capable of doing all three for sure. Yeah. I never heard of this. Interestingly. So 2039 launch date.
Yeah, she works at the Goddard Space Center,
Okay.
and they're proposing this, and next month, it's either, it's going to get funded or not. But they have no way of, getting it anywhere yet. They're just, that's why if they get it funded, it's going to take them 10 or 15 years to figure out how to get it up there.
Yeah, for sure.
So it goes from just from the name alone, it goes from the ultraviolet to the infrared.
Yeah, exactly.
But it's not X-ray like Chandra and what's the third big telescope out there?
Well, it won't do radio. Like radio is in Green Bank, like that radio telescope. That's a ground-based telescope, though.
Yeah. But Hubble is visual.
Hubble's optical.
Hubble's optical, and Chandra is X-ray, and there's a third one, and I can't remember its name or what it does.
Oh, Planck is Planck do cosmic microwave background? Is that it?
I don't know, but I've just been learning in geology how cosmic rays change the molecular structure of the atoms they hit on the surface of the earth, and that's how you can date surface rocks.
Oh yeah, that's a really cool property.
Yeah. What the hell? Yeah. No.
Was this the one you were talking about, Deborah? The Planck probe?
I don't.
It does microwave.
Okay. I maybe.
The order that she had of these was Hubble, Spitzer, Kepler, Tess,
Spitzer,
Webb, Roman, and Luvar. So I guess
what does a Spitzer do?
Spitzer is infrared, but it's
Infrared.
retired.
That's the one. That's what I was thinking. So that's up there already.
Yeah, and the Kepler and the Tess.
Yeah. So speaking of
Okay, so
flying
this
things.
neutrino thing.
Neutrinos?
What's with the neutrino wave that hit them in the beginning of the movie?
Oh,
These solar sails.
Yeah.
yeah. So solar sails, to the extent of my reading, are just collecting photons. I don't remember in the movie if neutrinos were hitting the sails and making them fly. If that were the case, that would be very unlikely.
No. There was there was the first catastrophe early in the movie was a
Solar
neutrino
flares.
blast. That
Oh, okay. Yeah. So
but whatever. Go ahead.
no, that's a good point. Because I'm a little bit skeptical of like whoever produced it, because neutrinos aren't really harmful. They don't really do a lot because they just pass right through things.
Mm-hmm.
There could be neutrinos flying through your body right now and you'd be completely unaware. They're so elusive and ghost-like and close to massless that we have to build giant tanks full of water just to capture one or two of them over the course of years. So
In mines.
yeah, they have to have these gigantic catchers to just, capture a few, to have the hope of capturing a few neutrinos. So for neutrinos to bombard you and have some sort of adverse effect kind of sounds far-fetched. But yeah, that's a good point. I didn't really consider that. I didn't really pick that up to how that's kind of unlikely.
Yeah.
So I'm reading this thing that says there's one small problem with these sails. Interstellar space has very little to none star energy. Despite impressive sun sails, the amount of energy produced by device would definitely be too small for the task.
Yeah. So yeah, solar sails are like borderline hypothetical. You can use them. They do work, but do they work to the point where like it's going to help us travel to other stars? Probably not right now, because you would need not only a lot of star energy, like you said, Stuart, focused onto one sail, but you need to have close to perfect reflection. And the ones we have right now don't quite do that. I think the best we can do currently is like 0.8. Let's see, where's the reflective index? I think I had something saved up here. Oh yeah, here it is. Oh no. I thought it was this page. Efficiency. Yeah, so assuming 90% efficiency, probably not going to happen. Constraints. I just read this. Okay. So aluminum right now has a reflectivity of 0.88 to 0.9. That's great, but it's not going to give us that 10% light speed that we need. We need full-on blasts of high energy photons into the sail, which is asking a lot.
How's gold?
Gold, that's a good point. Let's see, gold.
They seem to wrap a lot of space architecture in gold foil.
Yeah. So, oh, laser gold plating. I didn't read about this. This is cool. So this possibly has 97 to 99% reflectivity. Wow. Yeah. So they put this on aircraft and plotted the success with it. Yeah, maybe. So yeah, gold would be great. Probably just a little expensive.
But they use a lot already. Look at all the pictures of the satellites. They're all wrapped in gold foil. But it's not foil. Yeah. See?
Yeah.
Well, the other thing is, okay, so these things are capturing photons, but aren't there little bits of dust and asteroids and all sorts of things to rip these things up?
Of course. Yeah.
And the bigger, the worser?
That's right. Yeah. Space is very close to a vacuum, but we can't just trust that it's going to be literally smooth sailing to wherever you want to go. Because of course there's debris that's floating around not only the solar system, but interstellar space. Granted, once you leave the Oort cloud, you're pretty clear until the next nearest star, but getting out of the solar system is going to be a huge challenge. I forget I had this opened.
Gold coating, NASA spinoff. Gold coated mylar sheets to protect them from solar flares.
Yeah, okay, this is what I was looking. This was the scale that I wanted to use. Yeah, so 0.88 to 0.9. And then here's like the acceleration graph. And if we have everything perfect, can go up to, I think it's 180. Or no. 180,000 meters per second. So that's like 1/10 the speed of light. A little less than 1/10 of the speed of light. So you would have to have radiation at the same intensity hitting the sail the farther it gets. So that's really challenging because as the solar sail is receding from whatever star is powering it, it's going to lose that radiation energy. So I believe there should be a point when the radiation just runs out because it's so far away.
Yeah.
But I think you would have to go.
And what about reflection from of the solar energy light, whatever, from off of other planets? Or
I mean, yeah, it would help a
but
little bit.
that diminishes too.
But
with
so
distance.
yeah, it's so much less than just like getting it directly from a star.
So when a spacecraft, clearly they're powered with engines out of our, what was her phrase? Our gravitational well.
Yeah, well.
Yeah, I hadn't heard that before. Aki last week.
Yeah.
Yeah, but when you're traveling through space, are you still powered, or are you going on inertia or momentum rather? Momentum.
Yeah. So like Voyager 1, for instance, is not being powered anymore. It's just on its own.
Yeah.
So it has no friction. It's nothing slowing it down or stopping it. So it is just coasting out into interstellar space now.
But when we go to the moon, are we powered in some manner the whole way?
No. So essentially what we're doing when we get to the moon is we're just changing the orbit of whatever spacecraft to be not in Earth's orbit, but now to be in orbit around the sun. And
so
then
we use it gravity. Well,
so
go ahead.
Yeah, we want to escape Earth's gravity, but not escape the sun's gravity. So let me I wish I could like draw on the screen, but the sun's well is much bigger than the Earth's well.
Yeah.
We can escape the Earth's well just fine, but still be in the sun's well. And so once we escape Earth, we're free to turn off the jets, and now we're in orbit around the sun, and we have this curved trajectory. And well, this is to get to other planets. To get to the moon, you don't necessarily have to get out of Earth's orbit. But let's say we're going to Mars.
Yeah.
We just want to intercept Mars's orbit. So now we're in orbit around the sun, just like any other planet, let's say Mars is, and then we will meet at one point.
So once we escape the Earth's orbit, we're passively in the sun's orbit with a trajectory to intersect Mars's gravity well.
Exactly. Yeah. And
So
then
there's no, so
we get close enough to Mars and sink in it.
right.
Yep.
So the powering of these spacecraft it is really relatively limited, other than like positioning. What's the phrase for them? Positioning jets and.
Yeah. All you need, like if you're going to Mars, is rockets to get out of Earth's orbit. And then you're just floating. And then rockets to brake once you enter Mars's gravity well.
Right. Well, yeah. See, I always wondered about that because all the depictions, the rocket exhaust stops relatively quickly.
Mm-hmm.
It's not, there's no rocket exhaust on this Prometheus or its next generation.
Yeah, the only time they really utilized the rockets is when they landed on that, first like shot out of the orbiter, which was only like a second, and then they kind of like free fell into the atmosphere and just gently landed on the lake.
So, I have this quote here. I don't know if this is really a true quote or not, but it says the scene was explained by Ridley Scott in an interview. So he goes on to say, I asked one of the writers to put solar sails on the ship because it would look majestic, not because of any logical reason. I don't make movies to make sense or to entertain. I make movies to all people with cool visuals. How were they able to generate gravity on the ship if there's no power? Why would they even need propulsion drives to travel through space when they've harnessed the power of gravity? None of it makes any fucking sense, but it doesn't have to, because fans of my early work are still going to shell out cash to watch a streaming turd of a movie. I can't imagine that was a real interview, but
oh goodness,
maybe.
Except I totally agree with his perception of his work.
Well, that's a good way to put it. I appreciate that. So yeah.
Well, what about Star Trek? The Enterprise always has its nacelles going.
Yeah,
but of course they're always in warp speed. But
yeah, I feel like different movies just have different ways of propelling themselves. Like for what was it? The Star Trek 2009, they were using that warp drive, which folded space onto itself, and they can like ride it like a wave. And they weren't breaking any physical laws by doing that, by just manipulating space. And then there's others who, like my final point here was, doesn't matter how fast we go, because we could just sleep on the way there and wake up when we get there. And so I think we touched on this a little bit a few movies ago when we talked about like hibernation versus torpor. So I forget which one of the movies it was, but they froze themselves for a really long period of time. It seems like in this movie, they can control it however they want. They can just like go to sleep. All right, is it going to be 7 months or 7 years? Just set it and forget it. Really just climb into their pod and wake up when they arrive. And I did a little reading on cryo space travel, which is just like freezing yourself. I forget where I put it now. I have so many tabs.
It was 2001. They were in cryostasis.
I see.
Yeah.
Yeah, here we go. Okay, so this tab. Unfortunately, this is not in the near future. this is hypothetical, but it's not outlandish. We have so much to learn about the human brain and longevity. Right now, the average human lifespan is like 78 for men and 82, I want to say, for women, maybe 83. I think in the United States. So like, that's not even that great compared to like how long it takes to travel interstellarly, which is on the order of hundreds or thousands of years. So it's like, once we figure out this longevity puzzle, how can we elongate the human lifespan to begin with? Then we can start playing around. It's like, okay, let's see if we can preserve the cells as we are right now for a later time.
It's all in the telomeres.
Mm-hmm.
Ryan, do you know about telomeres? Stuart knows, right?
I heard the word, but I can't remember it.
So they're the little ends of the DNA helix molecules, of the gene molecules, that in some way keep the gene young in replication. And as they replicate, they don't deteriorate. But as we get older, our telomeres, Telemers, get shorter.
Mm-hmm.
And it's a consequence and of the aging process, but it also causes the aging process.
Yeah.
So
I've read a little bit about this in a book I read. We don't really have a solid consensus on why humans die. Like, what causes mortality, like the exact mechanism inside our bodies. Like, do our cells just get worn out and can't replicate as well as they used to? Or are we just more susceptible to cancer? Like, there's a hypothesis that says, even if you were in perfect health for all of your life, eventually, like, cancer will kill you. And I think for men, it's like, if nothing else kills you, prostate cancer will. Like, there's really nothing to stop cancer from taking over your body. And then a third one is like, I think just like our immune system is like compromised beyond repair, and we're susceptible to pathogens, I think. And there are probably many more hypotheses, like why is it that humans start to deteriorate around that 80-year mark?
The correlation of age and COVID, that was the main correlation.
Yeah, for sure.
I got to go. I'll see you guys in a couple of weeks. Let me know.
Oh, so yeah. So Ryan, what are we going to do without Stuart next week? Do you want to skip a week?
I can do one if you'd like.
So next week is the 21st.
Yeah.
Okay. So, well, can we not see an alien movie? Can we not?
Yeah, we'll switch it up a little bit. Yeah.
Yeah, leave Ridley Scott and his psycho cockroaches behind, man. Oh.
Okay. Yeah, I will let you know tomorrow.
Okay. Right, Stuart?
I think he's gone, but it'll just be me and you next week, I think.
Okay. Okay, I'm penciling you in.
All right.
Okay, life is in pencil.
Yeah. Did you want to still make a comment about like the aging thing?
Well, I think that, I haven't, read as you have, but I think there's a certain point where cells die, apoptosis. And it ain't necessarily cancer, and it ain't necessarily immunity. And I think things just stop working. And I suspect it has to do with the genetic loss of ability to replicate and repair cells and DNA. I mean, there are things, everything else does happen to us, but eventually, if those things don't happen, then we just deteriorate in some less specific way.
Right. All right.
Hibernating for 35 years. Oh my God. Until you get to the edge of the universe,
Yeah.
of the solar system. What
Mhm.
a nightmare. It would be full of nightmares. This COVID thing
Oh,
has
yeah,
me
for
full of
sure.
nightmares anyway. Yeah.
Yeah.
Hmm.
Yeah, well, that's all I had for my slides tonight.
Well, very interesting though.
Thank you.
Yeah. Okay, so we'll see next week, and I don't have anything to add because when I'm not watching sci-fi these days, I'm watching highfalutin, Shakespeare and opera. So
Yeah.
I'm not watching something that we could be talking about.
All right.
So I don't have any suggestions, in other words.
Mhm.
Yeah.
No problem. Sounds good.
Okay, well, thanks.
Of course.
Take care.
I'll see you next week.
Next week. I keep trying to recruit people, but here we are. Okay, take care.
All
Stay
right.
safe.
You
Okay,
too.
bye-bye.